So in the previous video, we created a model, we developed a model, we found we removed outliers, we found how many components is optimal, right? It was 3 components. And we also downloaded this model. So we click on this button, we download this model as a file. You can see it's a JSON file. What is inside? Well, inside you will find a lot of numbers. It doesn't matter actually. For you, it's just a lot of numbers. It's your PCA model, loadings, values for centering, scaling, and many, many others. But what is important, now we can use this model to test, to apply this model to a test set. So I go to test, I select model, I load it. Then you can see this is the file, model file, how many components in total, center it, and preprocessing was skipped. Now I need to select a data set. And you have 3 possibilities here. You can upload data set only with target class. You can upload data set with alternative classes. Or you can upload a mixed dataset where you have both target class and alternative classes, and this app will automatically recognize everything and provide you a proper, correct set of results. Okay. In the tutorial, I do it separately. So first I apply my model to the, you can see for the target class members, and then I apply my model to the alternative class members. I'm going to do it as well in this video, and then at the end I'll show you how to apply your model to the mixed data where you mix target class and alternative classes. So let me load the test target, this one. And then again, you can see automatically recognized everything. So this is it. So you can see this acceptance plot. You can show the names of the objects, right? You can see the distances, including the full distance. So you can see one is considered as extreme. So let me again look at it and see why it's extreme, why it looks different. You can see that, for example, you have this residual, which is a bit outside the common values, and also you can see it goes on kind of on the edge of all these intervals, right? Of all this different variation of the other residuals. For explain it again, it looks a bit extreme here, it looks a bit extreme here, and then this is the original data. Okay, so it looks a bit extreme, so therefore it was considered as an outsider, as a non-member of this class. You can also look at the distances, as I said. You can also look at the extremes. You can also look at the figures of merits. For example, this is a very nice plot which confirms that what we did with Procrustes cross-validation. So let me show you that, right? So this is Procrustes cross-validation. You remember it's generated validation set, and the real independent test set actually confirms our selection with 3 components. And of course, you can look at the scores plot. Okay. So from that point of view, this plot looks pretty much similar to what you have seen in the training set, but now it's a test set consisting of the target class members. Now let me open the alternative class only. So in this case, it will be this one. But now you can see that the plot is a little bit different. Why? First of all, you can see a very tiny decision boundary here, right? And there is no outliers boundary because we know these are already outliers, so to speak, for our model. These are alternative class members, right? So let me use a log transformation. So first of all, the good thing is that all alternative class members were correctly rejected by the model. That's good. But you can also see that they were split into 2 groups, aliens and external. The idea is following. Aliens are members of possibly the same population, which are the closest to the decision boundary. We use aliens to compute a special statistics, which is called selectivity. Okay. So selectivity, it's how well model can separate the non-target class from the decision boundary. Then the external are the objects which are very well separated, and therefore they shouldn't be considered to calculate the selectivity. While, for example, when we calculate specificity, it's the percent of objects correctly rejected. Then we take into account all these objects, and therefore you can see the specificity is equal to 1. Right. And then you can show the objects, and then you can see, for example, you can make the same conclusions as we also did in the tutorial, that, for example, timian and some other species are difficult to distinguish from the original oregano, although it is possible with our model, right? The rest is more or less the same. You can also look at the distances. You can look at the aliens plot. It's similar to extreme plots, but now it's a number of aliens. So number of aliens depending on the component. Sometimes it also helps us to identify how many components to use. You can see the figures of merits, which are a little bit different in this case. Instead of sensitivity, you see 2 figures of merit, specificity and selectivity. So you can see specificity and selectivity, and then you can see that specificity is pretty good. selectivity, okay, can be better if you increase number of components, but you remember it will affect the sensitivity, right? You can also zoom in to see it a little bit closer, and it's actually true for any statistic, for any figures of merits. And then this is a new plot. You can also see how selectivity depends on the choice of alpha. You can see here we have sensitivity, it's 1 minus alpha. Here we have minus selectivity. So this is a selectivity plot. It shows you the dependence between sensitivity and selectivity. It's very similar to ROC curve. You can also compute, for example, the area under curve, which is another way to assess how good your model is, right? So you can see, for example, if I change alpha, you can see what happens. I change the position of this line because this is the actual alpha we use, and this is the actual selectivity we have, 1 minus selectivity. You can also see how number of components changes it. So the larger number of components, the better selectivity is, but of course we know that sensitivity will be worse. And in contrast, if I use too few components, you can see, for example, if I use one component, the selectivity gets also worse. So this is a pretty good plot in terms of how well your model behaves against the strangers. And then, of course, we have a conventional plot for the scores. Now let me show you what's going on if you make the mixture, if you upload the mixed data set, where you have both target and the alternative classes. So first of all, you can see by default, this plot is shown for the target class members. But you can also see, for example, the result widget shows you two blocks. The first block is for members. It shows you how many members you have in total, how many is outside the decision boundary, so it's false negative, it's this one. And then also the sensitivity. So in this case, we have 18 minus 1 at 17. 17 divided to 18 will give you this number. You can also see this strangers. So how many strangers you have, sensitivity, specificity, also efficiency. It's a geometric mean of sensitivity and specificity. However, you don't see the strangers here because you simply need to switch them. Okay, so you can see members, strangers. So these are the strangers. So these are the same plot as we have seen before. You can also show all of them together, but in this case, they will be colored by the real group. You can see non-oregano, oregano. So this is oregano, this is non-oregano. All looks good, right? Distances is the same. Extremes only for targets. Aliens only for strangers. Figures of merits, in this case, it combines all of them, sensitivity, specificity, selectivity, but now you have a new one, efficiency, which is a combination of the sensitivity and specificity, and then you can see it's very clear again that 3 components is the best choice. It gives you the highest specificity, and then of course you also have selectivity and scores. Okay, and then of course we can also download the results. You can download also model if you, for example, adjusted the model. If you change the model, you can download the new model as well. Let's download the test results, and then let's look at in the downloaded file. So you can see these are the test results. Inside, it looks similar to what you have seen before, but because these test results are made for members of both target class and non-target class, it's a bit bigger. It starts with the same things, and then you can see it has objects in, out. It's a total number of objects that are recognized as members and as strangers. Then only members. You can see regular, extreme, outlier, sensitivity. Only strangers, in, aliens, external, specificity, selectivity. But it also has some auxiliary statistics. For example, you can see beta, the beta value. It's a chance to make type 2 error. And then you can see also 2 statistics. It's called non-centrality and scaling. These 2 statistics are used to calculate beta, and they are helpful if you apply the DD-SIMCA not for classification, but for example for limit detection, for detection limit. For computing detection limit, this is another topic, we will not cover it here. Okay. You can also see efficiency and additional actually forms, figures of merits, accuracy, precision, F1 score, PLR, and NLR. Okay. And then you can see also that the role is a bit different because now we have also non-target class members. You can see role can be alien, it can be external, and of course for the oregano samples, you can see it can be also regular and extreme. Then you can see the decision in, out, and all the distances. Okay. And then I didn't mention it, but it's very important that when you load data to your test set, it also should have these columns with class labels. It's also if for example, I reset the app, right? And if I load only the model, You can see this is written here. Column with class labels is mandatory. For training set and for test set, your CSV file should contain column with class labels. Okay. So that's actually it about how to test your model. And now in the next video, we will talk about how to make predictions.